The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everybody. Thank you for joining this week's Build Your Moldflow IQ. When is 3D mesh, or when is 3D too heavy? So this week we have Jeff Higgins that'll be giving the content, most of it anyways. And I just want to say a reminder here, if you have any questions, feel free to post those in the questions menu and we can answer those live. So before we get into the content, I just want to go through some quick slides that we normally do. So up until now, these are a list of the different webinars that we've hosted, which you can find on the Autodesk Sim 360 YouTube channel. And then we also post them, or we announce them rather, as you know, direct emails, which I think that's probably where the majority of everybody gets them. Then Twitter, Facebook, LinkedIn, and the forums. This week, or this month rather, we have the March Knowledge Network articles. As a reminder, these are the articles that the different tech specialists, such as myself, many of you have probably worked with Kristen or Paul, Bernd. So we write these articles based on some cases that we receive, and then we post those to the AKN or the knowledge.autodesk.com. And then for what is new in the news, for many of you who have posted or created cases rather, you've probably noticed that and you received an announcement that Subscription Center is no longer. Now we have Autodesk Accounts that's live, and what this is basically just a portal for all information, logging cases, downloading content, or downloading software. You can find different content in here, quick how to install the product, service packs, hot fixes, and so forth, and then create the cases, which is highlighted in the red blocks and the blue arrows. So, and then if you get stuck, you can always reference that article at the bottom there. So that's really all that I had this morning. With that, I'm going to go ahead and pass it over to Jeff, and if you have questions, let us know.
Okay. Thanks, Caitlin. I appreciate you going through all of that this morning. In fact, the Autodesk Accounts, I think, is actually a pretty neat new site, so I'm glad you brought that up. Today we're going to talk a little bit about 3D meshing and when 3D meshing is too heavy. Now I know that's kind of a little cliche catchphrase, but we want to talk a little bit about understanding dual domain and 3D meshes, which is really kind of the focus for this. And there are some true instances when 3D meshes can be too heavy, and there are more optimal ways of representing things. My name is Jeff Higgins. I'm a technical specialist with Autodesk based in the Detroit, Michigan area. Some of you may know me, some of you may not, but hopefully throughout the day you can actually see some of the things that we wrestle with and some of the things that we hope we can express to you about the different mesh types that we have in our Moldflow technologies. So one of the key things that we have to talk about as we go through this are some of the theories that we've got behind the dual domain and the 3D technologies. I want to cite some examples of both customer cases of dual domain and 3D successes so you can get a feel for how these are being used today. And then I want to wrap this up very quickly with a little bit of a comparison between the dual domain and the 3D models that I've actually run on my own. And this is, like I said, this is something where I wanted to basically illustrate some of the things that you can do with this, some of the challenges that you might have, and how these things would actually build together as you're gaining confidence and also being successful with our Moldflow technology. Now, I have to introduce this. And this is something that we have to keep in mind. Like any good FEA software, which is basically what Moldflow is, we're a finite element software. We're a bit of a CFD specialized code. We deal with plastic flow exclusively. You know, we have multiple mesh types, and any good FEA package will always supply multiple mesh formats to its users to give the most optimal representation of any type of model that they want to represent. In this case, you can actually take a look, and Autodesk Moldflow supports our mid-plane, dual domain, and 3D technologies. And this is a really good representation of how those technologies differ slightly. In fact, if you look at a mid-plane, it's very much the way the name describes it, is it's a center line representation of the model. You can see the triangulation or the triangular shell element there representing the center line flow of the plastic. In the dual domain model, it's still a shell element. It's still a two-dimensional triangular shell element, but it represents it three-dimensionally. And we're going to talk about some of the differences that exist between the different technologies as we go. And then the three-dimensional model that you see here on the far right is literally what it says. It's actually a volume mesh. It's a volume representation of the model where you mesh it through the thickness, and you can see literally stacking of elements through the thickness of the model. And that gives us a through thickness representation. Now, one of the things to be conscious of is every single one of these types of mesh forms have advantages and disadvantages. And those are some of the things that we want to talk a little bit about today. But let's get a kind of a clearer view of what this means to us when we start viewing these different types of representations of these models. For example, if we look at a midplane model of, these are all basically the same representation of this part. The midplane model looks basically like a flat piece of paper, like a flat sheet. And this is a traditional method that's been used for many, many years. In fact, this is basically how these types of technologies have started. And it gives a pretty good representation, although it can be sometimes very clunky, very difficult to create complex shapes. The dual domain gives us a very similar type of representation, but you'll notice if you look closely at this model here, you can actually see the representation of the surface flow, meaning that it's basically showing the overall three-dimensional movement as kind of a surface connection. So you can actually see the fluid movement, but you see it represented just on the skin. So everything inside is basically hollow. Although mathematically it exists, in between it's really there, but for visualization purposes it kind of looks hollow, and we'll talk a little bit more about that as we go too. Now the three-dimensional volume representation is exactly what it says. It's a true three-dimensional representation internally of what's going on. It's a true three-dimensional representation of mesh. And as you can imagine, that can sometimes generate a lot of mesh elements through the thickness. But so as we talk about these things, we're basically going to drop the mid-plane conversation off of the discussion today. We're going to focus primarily on the dual domain technologies that you've got here, and we're going to kind of work our way down through some of these and talk about why they're good, what they do well, and some of the things that we need to be conscious of as we kind of move forward. So when you look at the representation of finite element models, we've got basically three types of elements that exist inside of Moldflow today. We've got our beam elements that we primarily use for the representation of runner systems and for cooling lines. And you can see that here. It's a one-dimensional element. It's a beam. It gives us very good representations of flow in many cases, as long as we're not looking for too much detail in the runner system itself. It gives us a pretty good representation of what's going on. The triangular element, which is a shell representation of the model, gives us a fairly good representation of what's going on. It allows us to apply thickness as an attribute versus representing the entire volume. And it also gives us a good representation of the model, bearing that there are some caveats around the model itself. Now, the three-dimensional style element allows us to represent basically any type of format. It's a volume mesh. It's a tetrahedral element. And like any good CFD code will tell you, tetrahedrals are usually the best representation of fluid dynamics. So much like any good CFD code, we have kind of fallen in line with the tetrahedral element as the most accurate, most efficient way of calculating fluid inside of the volumes that we have, which are basically plastic parts. Now, having said that, things like runner systems and cooling lines can also be represented using three-dimensional elements, your tetrahedral elements. Even though that's not always a practice that's used, you can a lot of times mix and match some of these mesh elements together, meaning that I would use a beam element to connect to a shell-style mesh, which would be a dual domain or a mid-plane, or I could use a beam element to make my runner systems on a 3D model, or I could make everything in 3D. So sometimes there's some mechanisms that kind of mix these guys together, but inside of the software itself, these are the primary types of mesh elements that you're going to see and you're going to have to deal with. Now, when we start talking about dual domain, This is where the conversation gets really interesting. It is a three-dimensional representation of the model, but one of the things we want to be aware of is that this three-dimensional representation of the model is essentially a hollow representation. It's a shell representation, very similar to what a midplane would do. It uses a very advanced system of connection systems throughout the thickness of the part to measure what the thickness is and start applying thickness as a property. You'll notice that we can also get this representation of matching, and this is a way that we can ensure that we're getting a good connection from side to side in the dual domain model. So this allows us to then sort of diagnose whether or not dual domain can well represent the geometry that it's seeing, or the part in this case. And we want to see, in most cases, we want to see a lot of blue on those main walls. We want to see that they're matching up well, and that means that the measurements that we're getting in here are going to be accurate as well. Now, when we start talking about some of the assumptions that get made using a dual domain style model, they're very similar to the assumptions that would get made with a midplane, meaning that we assume that we have wall thicknesses that are well defined. Now, typically we call that a thin-walled part. It's not necessarily a good name for this, but it does sort of emphasize the same type of point, meaning that we want a well-defined wall thickness. Now, the normal definition to that is we want a wall thickness that is 2.5 times or greater in width to the height, or basically in the width to the thickness of the part, meaning that we've got a well-defined cross-section to the part. The closer and closer we get to what would be a square shape, the more abstract that is, and the more difficult it is to determine which direction the thickness should be. Because we're using these types of representations, the generalized Healy-Shaw model gives us a very good definition of laminar flow for non-Newtonian materials. We can start to build in things like the representation of the fluid characteristics, the shear dependence of the material. All those things can actually start to be picked up as part of this representation. And this allows us to basically extrapolate this in through the filling, the cooling, and a full representation of the model. It even allows us to perform full DOEs on these models as well. Now, in the upper corner here, you can actually see some good examples of where this type of model form is generally well accepted. Like, I can, on this part to the left, where you can see my mouse moving, I can see that it's got some very well-defined thicknesses in it. That means that I can well represent this using a dual domain model, using a midplane model. Dual domain, probably the easiest way to represent this, but as I start approaching things that are thicker and more abstract in shape, it's harder to determine what a thickness would be. So this is a good example of where 3D starts to really excel in the world of analysis. So let's take a quick view of what's actually happening inside of a dual domain model. Right? So inside the thickness of a model, basically what we're doing is we're defining the top and the bottom elements on the model itself. And then we're mathematically dividing this up through the thickness. Now, this is very similar to what the midplane would do. It would represent the zero, or the neutral center, and then it would extend the thickness out in either direction. In this case, we're building the thickness internally. It gives us a little more accurate representation than a midplane, so it does do a pretty good job. The nice part about doing this is it's a mathematical representation. It allows us then to divide the thickness up into any number of laminations that we want. The default, by the way, is 12. We can set it as high as 20 if you want to go to that type of resolution. It really is up to you. Now, the same thing holds true for a beam element. A beam element is sort of the same type of thing, only it's a radial representation of layers. You can see how they sort of radiate out from the center. Now, this means that we don't have, say, a core and a cavity side like we do in the dual domain model. We just have a positive direction of diameter that's being represented. But in this case, on the dual domain, you can see we identify what the core and the cavity sides are by the plus and the -1. The beam element actually just goes to +1. We can see a good representation on these geometries, again, by looking at the match ratio. And we've got some pretty good rules of thumb that go along with this. And we want to look for about an 85% match, meaning that 85% of these elements match on the wall so we can get a good measurement of thickness. We want to make sure that it's about 90% for warp. And you can see that as part of the statistics window inside of Moldflow. Now, one of the things to be aware of is this is a rule of thumb. There are diagnostics in here that you can check and make sure that you've got a good representation. Those percentages are really just there to start pushing you in the right direction. And we can talk more about those if you want at some point in the future, but these are the directions that we would start pushing it. And being able to visualize that match and making sure I know where I've got good match and good representation is extremely critical. When I start getting into representations that are extremely more abstract or more complicated or what we would call chunky, it's very difficult to figure out where either the center line would be to create a midplane or where my measurement directions should be in order to use dual domain. This means that it's very difficult for dual domain to calculate the thickness accurately, and it's probably a better solution to go more towards a 3D. So when we start defining these things like thin-walled, it's actually a well-defined wall thickness that we're looking for. And if this guy didn't have all these extra little features on it, we'd probably get away with even dual domain on this. So here's another good example of a really kind of a complex shape on the body of a part where dual domain is trying to measure the thickness, and you can see how complex that thickness representation is, how difficult it is for it to kind of figure out which direction they're going. So some of these more complicated shapes really should be represented in 3D. Now we start talking about the three-dimensional elements. Right? One of the things that we want to express is that this is really a volume representation. It actually meshes three-dimensionally. It does everything through the thickness. And we normally say that this is for sort of a chunky representation. And it's based off of a full 3D Navier-Stokes calculation with some special algorithms that we've developed in order to help things like fiber orientation, fluid movement of plastic, shear dependence, and so on. We can even start adding things in like inertia and gravity into our three-dimensional meshes. So we can start calculating all of these things. The great part about a three-dimensional model is we can represent anything. We can represent the thin parts, we can represent thick parts. But the thing to keep in mind is we have to think about how many elements that we're going to create in order to do this. And that's where this becomes extremely important. So in 3D, rather than mathematically dividing this up into a calculation of thickness, we literally have to mesh all the thickness. So we mesh rows of elements or rows of information through the thickness. The default, by the way, is 6. Now, if you remember, we were talking about dual domain. In dual domain, our default was 12. Our default was twice the laminations through the thickness as to the layers that we have in 3D, which means that we can pick up more resolution in freezing, in shearing, all the things that happen through the thickness mathematically, as long as we get a good defined wall thickness. Normally, if we start getting into fiber orientation, we suggest 8 or more rows through the thickness, and you can start to see how this would start to develop. As you start adding elements through the thickness, you're adding your mesh count, you're adding complexity to this, really start adding the detail in. So basically what we're getting to with all of that explanation of what these different models are doing is we're very quickly starting to describe that we have the appropriate mesh for the appropriate model. So we've got the appropriate mesh type to represent just about anything. So if we look at a dual domain model, it's an accurate representation for well-defined wall thicknesses. It accurately represents the shear that happens in the part, gives me a good representation of velocities and temperatures, and it's an accurate advanced measurement system for the thickness of the part. In fact, it allows us to get some of the flexibility of what we used to be able to do with midplanes into a three-dimensional representation of a model. Now, having said that, remember we started getting into those more abstract shapes, the more complicated geometries like you see on the right side here. It's a little more difficult for dual domain to try to represent. It's more complicated to measure that thickness. Well, this is where 3D really starts to excel. It can represent anything. It can represent the internal volume. It's perfect for any thickness. Represents the entire volume. It requires that you mesh everything through the thickness. And you can create a very large mesh with equivalent resolution through the thickness in order to represent what's going on. So if you're using a dual domain model like the guys at Bayer, you can actually see that they did this on a well-defined wall thickness part. They were interested in the rib on the inside of this component. They wanted to know how much it was going to warp. And they used a dual domain model to represent this. This means that as they were going through this process, then they could actually take this through the flow and the cool and the warp and the fiber orientation calculations, and they could start to make some significant reductions in the amount of time it was going to take to optimize this part and represent it using a mesh that is more optimal for this particular design. Here's another great example. Audi took one of their cylinder head covers. It's, again, a well-defined wall thickness, something that's easily representable. They took it into the Moldflow software. They used a dual domain mesh type. They took it through flow and cool, optimized the wall thickness, reduced the amount of mold changes, and actually developed a better part using a dual domain. Now that doesn't mean that there isn't a time to use 3D. 3D is extremely critical for warpage when we're starting to get into some of these thicker parts. In fact, here's a good example of a part that was more complicated to represent. It has a very thick geometry to it, very complex, and this particular customer wanted to mount this control panel internally, and they wanted to make sure that they could accurately represent what it was doing. So they used Moldflow, and they used a three-dimensional mesh type in order to represent this geometry. And here's one more example. We're looking at a three-dimensional model where it was a little more complex. The area around the outside edge of this would have been a little more complicated. We were getting poor match ratios with dual domain. 3D became a much better solution to represent everything through the thickness of the part, represent that volume, right? And they basically reduced their development time by about 20 days by doing this, saved about $60,000 on one part just kind of going through this process. So really some good examples of how you can use each of the different mesh types in an appropriate model in order to represent what's going on. Now, one of the things that I wanted to talk about was we've had these conversations come up in the past. Now, remember, we talked about the fact that 3D uses 6 layers through the thickness as a default, 8 if you kind of bump it up a little bit. Dual domain defaults to 12 laminations through the thickness, twice the resolution. Now, that doesn't mean that I can't do the same things with a 3D model that I can with a dual domain. I absolutely can. I can set 3D to have the same resolution as my dual domain model. I can set it to do the same things. And some of the things that are limitations to dual domain then sort of go away. But we have to take a look at what is the change in accuracy, what is the comparison that we're starting to get into when we start looking at these variations in model types. So I did just that at one point. I decided to take a look at one of my parts, and I wanted to take a look at it from the standpoint of dual domain and 3D, and I set them to be equivalent. Right? I can do that, right? Because I've got 12 laminations through the thickness in dual domain. I can create 12 mesh layers in 3D. That creates the same apples-to-apples comparison. Now let's take a look at what happens on my part. When I did the initial fill comparison, you can actually see that my end-to-fill locations are identical. You can see that my part designs are identical. And when I started to take a look at the pressure comparison between my dual domain model and my 3D model, the differences that I got when I set these to be the same on a model that was appropriate for both was very tiny. It was probably well within what would have been the variation of an injection molding machine. But I'm looking at about 4,600 PSI in both. There's a 50 PSI difference. That's 5 hydraulic PSI on the machine. That's almost nothing. I mean, most injection molding machines will vary anywhere from 10 to 20 PSI on hydraulic pressure from shot to shot. So I'm well within the variability of an injection molding machine at this point. I've got good consistency. I've got a good representation between these models, right? And if I start to take a look at things like how do my warpages compare between the two models, right? I actually did the same type of comparison. And I went through almost every single result on this particular part just to sort of illustrate if I do things in an apples-to-apples basis, how good are my representations on my parts, right? And here I can see my max deflection when I use dual domain is about 0.02 inches. When I do my max deflection in 3D, it's about 0.02 inches. I'd say that's pretty close. In fact, again, we're probably within the shot-to-shot variation of the machine at this point when I start looking at some of that variability. So what it really comes down to then, and I actually wanted to redo this. In fact, as a part of doing this, I was thinking about doing my presentation today. I actually decided to rerun these last night in current versions of the software. So the stuff that you're looking at is actually stuff that I just recently ran. I just reran everything and updated these images. So you can actually see the date, right? It was last night that I reran these. One, to get the timing. I wanted to show what some of the differences were. You notice it's about 4 times longer to do the 3D mesh to get the same type of accuracy. And on a part that was this small, it took me about 6 minutes with a dual domain to run. It took me about 22 minutes. So you can imagine what we're talking about when we start getting into bigger and bigger and bigger models, right? So if I can achieve the same level of accuracy using a dual domain or within a good tolerance value, it's advantageous to me to start making decisions early in the process by using that same type of dual domain model. So basically what I'm coming down to, and this is the slide that I had shown earlier, right? In summary, we have the appropriate mesh for any type of model. And we have it that you can get efficient, accurate answers out just by creating an accurate representation of your model. Whether that be dual domain or 3D, it's completely up to you. Like I said, I've got some folks that have told me everything in the world should be 3D, and I can actually set 3D to give me the same accuracy through the thickness with the representations, with the layers and everything that my dual domain does. And I can get that same level of detail out of my 3D model. But again, if I can do it with my dual domain model and I can get an accurate representation, maybe I should consider just being a little more efficient. So, I'd like to thank everybody for spending some time with us today and going through the presentation with me here. And I'm not sure we can do this, but Kate, are we capable of actually opening this up to questions at this point?
Typically, we don't just open it such that everybody can speak,
Okay.
but if they have questions, I have myself, Kristen, have the questions panel open. I don't know if you're able to see that or not, but if anybody has questions, let us know and we can ask them live.
Actually, I do see some popping in here, so let me see if I can answer.
Perfect. Yeah.
I'm not even sure what I don't think GoToWebinar will actually show this on the screen, so I might be the only one that can see it. It says upon completion of this webinar will be posted on YouTube. Well, Kate, I think you said earlier that everything will actually be posted someplace else, and I see that you responded to Steve for that, and I do appreciate it. What is the definition of the Healy-Shaw model? Thank you for including that link. For anybody else who's wondering what Healy-Shaw is, it's a well-accepted fluid dynamics code for 2D flow, meaning that you use a two-dimensional mesh to represent it. It's something that's very common in the world of CFD when you're representing thin volumes that you're actually pushing any type of fluid through. Healy-Shaw is just sort of the mechanism or the basis of that type of calculation. And of course, we build some of our own plastics technology on top of it. I saw a question here that says, sometimes I see that the 2D calculation can take longer than 3D. That's actually a common response that I do get. And the reason that you'll see that is if you don't do that apples to apples, and pay very close attention to what I did in my presentation, as I set my 3D model to be the same level of accuracy as my dual domain through the thickness. And that's something that's very important. If I set my 3D model to be just 6 layers through the thickness or just 8 layers through the thickness, again, you're reducing the resolution through the thickness, and the opportunity there is to actually get something that will run in almost the same time or quicker time than the 2.5D mesh, but you're doing it with less accuracy through the thickness. So what I did was an apples-to-apples comparison. It is possible to get faster run times out of 3D, again, by reducing accuracy. It'd be very similar to taking your dual domain model and meshing it coarser and telling me that it could run faster. It's the same type of idea. It says, I've got another question here from Matt. It says, how is it possible to connect 3D mesh to dual domain? Is it a good practice to do so? So there is a little bit of a catch to this. You would never be able to, say, connect a dual domain thickness to like a 3D runner system. If you wanted to go to, say, a 3D runner, you would probably do the entire model in 3D. What you can do in some cases is you can connect what are two-dimensional attribute model portions to a three-dimensional model, meaning if the part is represented in 3D, you could potentially connect, say, a beam runner system, or you could put like a dual domain or a mid-plane fan gate on a 3D model. So there are mechanisms to connect those together. It is completely acceptable to do that. You just have to be conscious of how you're connecting those together. So that is an acceptable practice, so feel free to do that at any point. Actually, asked what the number of elements were in this example. And actually, let me see if I can pause this for a second. I'll see if we can pull this up, and I will show you the 2 models that I actually ran. I want to say that the dual domain model was about 25,000 elements, and I think the 3D model was about 500,000. But I'm doing that off the top of my head. I actually just got another one here. Can I mix 3D, dual domain, and mid-plane? Yeah, you can. Again, it's going to have to be a 3D part model with a dual domain or mid-plane runner system. But yes, you can mix those together. I think the last question we have here is, can you tell me something about the contact diameter when I do not model the gate? Also, I do not see the difference if the part is an injection point and change the contact diameter. Okay, so you're basically asking about the contact diameter of the injection location. So when you create a three-dimensional model, you have the opportunity to create what is known as a contact diameter, which basically is a shadowing of the diameter onto the elements of the part. What that does is it's basically being used for the initial shear of the plastic into the part. It's not really being used for much beyond that. What you can do, though, is you can change that diameter and change the shear, which will change a little bit of the temperature impact of the part as it goes in initially. If you really want to see the impact of, say, the runner system or gate freeze, the contact diameter is not going to do that for you. It's literally just the initial shear into the part. You really do need to model the runner system in order to see that. So you probably wouldn't see too much of an impact, but you would be able to see something there. One last question. It looks like, can I refine the mesh at some location? Yes, we do have mesh refinement capabilities built into the software. You can refine mesh locally. So you can actually do what's called a remesh area inside the software. One of the most common things to do, though, is actually to remesh around an injection location. So just to place an injection location on the part. We've got some really nice algorithms built into the software now where you can actually import the CAD model, place the injection location on the model, and then mesh, and it will automatically refine around the gate. And you can even define some of the refinement around the gate also. So that is an automatic thing that's actually been built into the software now too as well. So when you start to do things like the shadowing that was asked about earlier, it will actually more accurately shadow that shear onto the elements, more accurately shadow what would even be the gate orifice from a beam element onto the part, better represent that as well. We've got another question. It says, can I change the number of layers in 3D for an assembly? Does it change the number of layers of all bodies? Yes and no. So there are some mechanisms that you can change only some of the bodies or all the bodies. If you do it as sort of a global, you would actually set all of the layers to be the same right away. Now, what is a common practice oftentimes is to create, say, a dual domain mesh and actually have an insert as part of that where you actually align the elements in the insert. Totally appropriate in that case to create different meshes. You would want a very accurate through thickness model for the plastic portion, but maybe something a little more coarse through the thickness for the structural or for the insert portion of it if you're doing a core shift analysis, let's say. So in that case, one of the things that you might consider doing is meshing them independently, pushing them together. You can actually mesh them together and control them a little bit that way too. So there are some mechanisms built into the software where you can control that as well. How can I export to Abacus? That is probably another discussion topic we should have here. But there are some mechanisms to export to Abacus. There are about 3 mechanisms built into Moldflow today. One of them is our legacy translator, which actually uses the existing mesh from Moldflow, which is usually very heavy for Abacus. We usually have more elements than Abacus really cares about. So that model would be very heavy and take a long time for Abacus to run. And that's our legacy translator that you can actually use a script to basically export the information from. As part of Moldflow today, we also include what is known as structural alliances, Moldflow Structural Alliance. That allows you to send a lot of the linear property data out to Abacus. That actually comes as part of your Moldflow licensing today, so you're more than welcome to use that. What we're actually working on right now is a significantly better option. We actually have a product based on our Sim Composites technology, which is allowing us to map our Moldflow meshes to structural meshes, and they can be in dissimilar locations. So you could have something in body position in an assembly, for example, and something in tool position in Moldflow, and we can actually align those, map the fiber orientation, map the residual stresses, map that data over, and do a full nonlinear analysis. That's actually part of our Sim Composites tool, which I believe is going to change names to Helios in April, which I believe we call Sim Composites Advanced today. The extension to that comes with the Sim Composites functionality is what we call Advanced Material Exchange, and that's probably our most comprehensive way of sending Moldflow data to Abacus. One more question says, when meshing the cooling channel conformal cooling element becomes complicated to generate over 5 million elements, what would you suggest to reduce the cool FEM or calculation time? There's a bunch of ways that you can go after controlling your mesh. And one of the things to keep in mind is you can generate a lot of mesh when you're going into conformal cooling or even just the cool FEM capability, that mold mesh doesn't necessarily control the amount of time it takes to calculate things. That mold mesh will control the amount of time it takes the cooling analysis to run. That cooling data will then get mapped over into the plastic flow analysis, the filling and packing analysis. So the big influence you would see there would be only on the cooling portion of it. A lot of that data would get mapped over. There's a couple of ways of modeling the cooling system. And you can either model the cooling system much like I had shown in some of the slides I had where it was a beam element. You can also model the cooling system as a three-dimensional element. It's up to you how you want to do it. Probably the most common way to do it is with a beam. It seems to be faster. A lot of times in tooling data, things like the baffle blades are missing. You'd have to model those in manually in order to get the up and the down flow in the three-dimensional channels. So there are some mechanisms that you can use in order to represent those. But for the sake of runtime, unless you're dealing with something that is really a free form or a sort of an arbitrary shape cooling channel, I would probably suggest going to the beam element. There's also channel-style conformal cooling, which actually seems to be more common now, which you can still represent with a beam element. And it's a very good way of representing it. That'll help keep your calculation time down a little bit. Wow, I think I made it through most of the questions. If there's anybody else who has a question, feel free to kind of plug that in. Otherwise, I will thank everybody for joining today. I'll stick around for a couple minutes here, but I appreciate everybody sticking around. I hope this was helpful for everyone, and I hope we covered a whole bunch of content in a very short amount of time. So I appreciate everybody sticking around, and let us know if there's any questions or anything we can help you with in the future to better understand this.
Yeah, thanks, Jeff, for joining today. I think this was a nice continuation of we did a meshing based off of the AU presentation a couple weeks back, so I think this was a good continuation, definitely. Mm-hmm.
Cool.
Yeah. Yeah, it doesn't look like any more questions are coming in, so I think with that we'll go ahead and wrap it up. Just a reminder, you will receive an email for the YouTube, and so you can check it out. And if you have extra questions, you can either submit those to the forums or create a case using Autodesk accounts, and we'll happily assist you. Thanks, everybody.
Thanks, everyone.